So let's take a look at a couple of examples. The first one, we have a 4 kilogram bar. It is released from rest. This is where it is at the beginning. It's released from rest. One side of it is pinned to some fixed structure, some ceiling or roof, some ceiling or some fixed support. Right. The other side is attached to another pin, fixed pin, using a spring. We release it from this position, position 1. The bar rotates and goes all the way to position 2. Well, the spring is more stretched now, and we're asked to find, if this bar goes from point 2 to point 1, or position 1 to position 2, sorry, what is the magnitude of the bar's angular velocity when it's in position 2, right? Now, well, there is no non-conservative force. We don't really have any external force or any friction. So what we have is just the work done by gravity and the work done by spring. So we can actually use conservation of energy. So T1 plus V1 is equal to T2 plus V2. Now, at point 1, well, we're going to look at different terms on this equation. At point 1, well, it's released from rest, so I'll put it this way. At point 1, well, T1 is 0 because released from rest. V1 is 1 over 2 K S1 squared. Right? How much the spring is stretched or compressed? Well, let's see. We are told that the unstretched length of the spring is 0.4. And we see here that the length of the spring is 0.6, meaning that the spring is actually stretched 0.2 meters. So that'll give me, let's write it this way, 1 over 2. Well, I'm given the value of K is 20 times, well, the S1 would be 0.6 minus the unstretched length, which is 0.4 squared. That'll give you 0.4. Well, this is energy, so the unit is joule. 0.4 joule. Now, at point 2, let's see what's going on at point 2. Right, you want to find out the value for terms on the right side. Now, T2, well, it's a rotation about a fixed axis. So that'll give me 1 over 2 I, mass moment of inertia about the axis of rotation, which is A, omega squared. And potential energy at point 2, well, two things happen. You realize that I took the datum for the first part as here. So this is my datum because I pretty much said the kinetic energy due to, or the work done by the gravity at point 1 is 0. So this is the, let me write it the other side so I can use this side for a different purpose. This is the datum, right? Or where the I consider this 0 potential. Now when we go to point 2, well, here is a slender bar. It's 4 kilogram. Like we know the length is 1 meter. Let's say the center of gravity, well, it's exactly in the center, in the middle, so 0.5 from away from point A, and here 0.5 meters here. So what happens is that the center of gravity falls h amount, whatever that h is. And now this is negative because it's below the 0 potential line or datum that I consider. So this gives me, let me put the whole thing, 1 over 2 K S2 squared minus, well, mgh. It's minus because it's going below. Now, what is h? Well, we have to find out. Let's take a look. Well, here we need to find out what IA is, mass moment of inertia about point A. We need to find what is S2, how much the spring is stretched or compressed. And we also have to find out what is H. So let's go one by one. Let's start with S. Well, let me go with IA, the terms from the beginning. IA, well, it's a bar. The mass moment of inertia of the bar around its center of gravity is 1 over 12 ml squared. and we are looking to find mass moment of inertia about point A, or axis A, which is 0.5 meters away from the axis passing through the center of gravity. So that'll give me md squared, and d being 0.5. So I can plug in the numbers. 1 over 12, the bar is 4 kilogram. The length of the bar is 1 plus 4 kilogram times 0.5 squared, right? The distance between two axes. The next thing I have to find out is S2, right? How much the spring is stretched or compressed at point 2. Well, it seems like it's pretty stretched. Now I need to find this length. I know the unstretched length is 0.4. I need to find this length now. From some old math, I write it here. If I look at this triangle, it goes this way, and there goes this way. So as good as I could make it. So this side would be 1.6 meter. This is the triangle formed by the whole system when we are at position 2. This is 1 meter, this is the bar. This is point A, and here are two other points. Now I know this is 60 degrees, so I want to find out what this length is. If you remember, when we wanted to find the length in front of an angle, well, if we consider this A, B, C, C squared would be A squared plus B squared minus 2 times AB cosine the angle between those two sides. So I'm just going to use that equation. So I'll say, let's call this, well, this as, I don't know, let's call it R. So R would be the square root of, because R squared is equal to 1.6 squared plus 1 squared minus 2 times these two sides, which is 1 times 1.6 times cosine the angle between, which is 60 degrees. So this gives me R, as if you do the math, we're going to get 1.4 meter. Now this is the final length. If you know the final length, you know the initial or unstretched length. Sorry, let's put it that way. Unstretched length. So you can actually find out what the S is. Right? So 1.4 final length minus unstretched length, which is 0.4. This gives you 1. The last thing is h, the height. You can find the height too. But what is this height? This length is 0.5. And look at this height there. Let's look at this triangle there. Now this is 0.5. We know this is 60 degrees. So in this right triangle here, we want what is the length of the opposite side. So opposite side would be 0.5 sine 60 degrees. That'll give me 0.5 sine 60 degrees. There goes these three components. So knowing those, you can actually put them together. You can find T2 and V2. Let me plug them in. From there, we'll get T2 as 1 over 2. Well, if you do the calculation for IA, you'll get 1.333 continuous. It continues squared, which is going to give you about 0.667 omega squared. And you'll get V2 1 over 2, well, K we know is 20. S, we found it, is 1 squared minus 4 times 9.81 mg, and H we found to be, this becomes 0.433. So this becomes, raise that, this becomes 0.433, right? This gives you minus 6.99 joule. So from all these, from there, let me put it this way, well, T1 plus a V1 is equal to T2 plus V2. So 0.667 omega squared is equal to, I'm going to take this V2 to the other side, so it becomes positive 6.99 plus 0.4, and we can solve this and get omega, which is 3.33 rad per second. And that's the angular velocity of this bar. That's what we were looking for. Okay. Next example. Next page. We have two gears. They are interacting. Obviously, they are engaged. Then we know the moment of inertia or mass moment of inertia of these two gears. They can freely rotate around the pins they're attached to, which means there's no friction here. The gears are at rest when a constant couple M, this couple, is applied to gear B. So M is applied to gear B. Neglecting friction, wherever can be a friction, just neglect that. Use the principle of work and energy. This is pretty straightforward. The problem tells us what to use to find the angular velocities of the gears when gear A has turned 100 revolutions. And we also know the mass moment of inertia for each gear, right? We're given those values. So, well, we have an external couple M, so here we can't actually use conservation of energy, the expression for that. So we have to go with principle of work and energy because that couple is doing some work. T2 minus T1. Now, U from 1 to 2, let's put it this way. I'm going to split it into, let's see, U from 1 to 2. I'm going to split it, U from 1 to 2, done by gear 1, plus U from 1 to 2, work done by gear B. Now, gear A, I have two rigid bodies. Well, going from 0 to some theta A values, md theta, since there is no couple applied to gear A, so the work is 0 there, work done by some external force, or couple. There is no external couple applied to gear A. Keep in mind, the couple is applied to gear B. So for gear B, you'll get, well, start from rest, so 0 to some angle theta B is md theta. Let's see, let's find out what theta B is. Well, we know the information we have is that gear A turns 100 revolutions. So let's see. If gear A turns 100 revolutions, let me put it here, separate this. So theta A, well, each revolution is 2 pi, right? It's a circle. So 100 revolutions gives us 200 pi, right, for gear A. Now, well, gear A and gear B are engaged. So there is a relationship. It's pretty much the same as the velocity, angular velocity. If you remember, we were talking about angular velocities. We said whatever is the angular velocity, well, in this case is the displacement, rotational displacement, because they're pretty much the same. We just take derivative with respect to time. So theta B, the amount gear B rotates is over the amount gear A rotate is equal to the radius or diameter of gear A over the radius of gear B. So there is an inverse relationship, right? And you can guess that. Theta B, when theta B rotates, theta A, for one rotation of theta B, theta A rotates more, right? Because it's smaller. It's pretty intuitive. And you have to go with RA over RB. This is a solid relationship. It is always valid, right? The rotation of this gear over the rotation of this gear is equal to the radius of this gear over the radius of this one. So when you have two gears engaged. So from there, you can actually find theta B, well, pretty straightforward, RA over RB times theta A. If I can do that. Well, you plug in the numbers. RA is 60 millimeters. RB is 90 millimeters. So it would be 60 over 90 times 200 pi. That'll give you 418.9 radians. Okay, so keep this here. So we can use that. Now, U from 1 to 2, well, the first one is 0. The second one would be M theta A minus 0. Sorry, theta B. We're looking at B. Let me just write it. Oh no, I actually wrote it here already. So U1 to 2 A, U1 to 2B. Well, the first one is 0 plus the second one, M is 2, is constant, comes out, times theta B minus 0. Well, this gives you 2 times 418.9, which gives 837.8 joule. So this is U from 1 to 2. We got what we needed for the left side of the equation. For the right side of the equation, well, you have to look at the kinetic energies, right? Let me go to the next page. So in terms of kinetic energy, well, I'm going to split it into two components for gear 1 and gear 2. Well, T2 is equal to T2 for gear A plus T2 for gear B. So T2, well, T1 is also 0. Keep in mind that the motion starts from rest, so I don't really care about T1. T2A is equal to 1 over 2, well, IA, otherwise mass moment of inertia at point A, omega A squared, and T2B, oops, T2B is equal to 1 over 2 IB omega B squared. So this would be 1 over 2, well, I'm given the value of IA, which is 0.002 omega A squared, and this is 1 over 2, the mass moment of inertia for the second gear, or gear B, is 0.006 omega B squared. Now, I can also find the relationship between omega A and omega B, right? We've seen this actually before. We talked about this. Omega B over omega A, right? The inverse relationship between the velocities and radii, right? RA over RB. So I'm trying to just write one velocity based on the other one, so I only have one unknown in this equation. I only have one equation at the end when I put things together, so I can only afford one unknown. Omega A. This is something that we'll use. Now, putting both sides together, let's call this 2. Let me go back to the first one, and let's call this 1. Right? Putting these two together, next page, 1 and 2, we'll get, well, that would be, you know what, let me write T first, and then use that as the second equation. Now it's a little raw. So T2, right, it becomes, well, 0.001 omega A squared plus 0.003. Well, omega B would be the ratio of radii, 60 over 90 squared, omega A squared. Right? I just replaced omega B with RA over RB omega A. And that's a square, so I squared that. Now this I call equation 2, and 1 and 2. Then from there, I just put them together, both sides of the equation. On the left side, we found the work done by the moment. It was 837.8. On the right side, I'm just going to put everything and take omega a squared out. 0.001 plus that would be 0.003. Well, 6/9 squared divided by omega a squared. Well, from there you can actually find omega a easily. Omega a would be 599.2 rad per second. Right? That's the angular velocity of gear A. Now for gear B, well, we already know the relationship between omega A and omega B. We'll just plug this in, I'll get omega B. Right? So omega B is RA divided by RB times omega A. You do this math, well, you'll get omega B. You have everything you need. 399.48 rad per second. And that will be the angular velocity of gear B. You were asked to find the angular velocities for these two gears.